Me. Hello and welcome back to Calculus 1, section 2.5, limits at infinity. Now these are different than the previous section. Limits at infinity is now infinity is the input and we are looking for a finite answer, finite number. So the limit that we want to work with now looks like this. Limit as x approaches positive or negative infinity of f of x needs to have a finite number as an answer. So that's the form for 2.5. An example of this would be again limit of 1 over x as x goes to positive infinity is 0. We can see that from the graph. As the red arrow is going to positive infinity, as x goes to positive infinity, the y value drops to 0, right? Because the answer of the limit is the y value of the function. So the limit as x goes to infinity is, for this particular function, is 0. Another example of this would be the decay exponential function, right? Decay function. So if you have limit of e to the negative x as x goes to positive infinity is also going to be 0. And we know that the decay function looks like this, right? Going to 0 as x goes to positive infinity. So that's it, we're done. That's 2.5. Now, what? Guys, it's calculus.
I like this part.
I know, right? This is it. So now we do application, right? This is the concept, and I hope you get the concept, right? So as your x goes to either one or the other infinity, y will go to either a number or something. Let me give you one more example. Logistics function for population would have a graph that would look like this. You start with initial population, and then that population grows exponentially, and then it levels up at the number that we call K, carrying capacity. This planet is, well, number one is round. This planet is finite in its surface area. You have continents with land on which we build houses because we are not fish. And on that amount of land is finite and in time is diminishing because the deserts are spreading and the seas are rising because the poles are melting. So it's negligent, but it's there. So we have finite amount of resources on a finite surface. Therefore, there has to be a critical number, which we call carrying capacity of the planet. Now, as you let population x to go, as you let, time to go to infinity, population function of time has to settle down to the carrying capacity. of the planet. You cannot fit more population than what planet can sustain. Now, scientists are all over the place what that number is. Bounces between 10 billion and 15.2 billion. We are at 7.4 billion, and with exponential growth in population, we are doomed in next 60 to 100 years, no matter where they park the number, it doesn't matter. Which is why Elon Musk wants to get the hell out of here as soon as possible, so he's working on his rockets, right? And he might pick one of you to bring with him, so he can still be superior, right? So these are the examples as x or t as time, right? As these independent variables go to infinity, your answer could become a 0, or it could become, in this case, let's say 12 billion, right? And that's a finite number. That's what we are looking for, right? We're looking for a finite answer. Now, we are going to define horizontal asymptotes to this. So we are continuing with our pre-calculus, redefining pre-calculus. So now, horizontal asymptotes. A function f of x has a horizontal asymptote at y equals L if or when the limit x goes to positive or negative infinity of f of x is equal to L. We started with this statement. This was the first thing I wrote. So I have now the way to check if something is a horizontal asymptote. Say I have good old function 1 over x as x goes to infinity. Well, we know it's a 0 there. 0 is a finite value. Therefore, horizontal asymptote at y equals 0. Limit at 1 over x squared as x goes to infinity is also 0. Therefore, horizontal asymptote at y equal to 0. Now, you might have some spicier examples. Say, limit of 3x squared plus 9 divided by x squared plus x minus 6 as x goes to infinity. You might remember the rules from pre-calc. Those still hold. If you remember the rule for rational functions like this, the rule said if you have the higher exponent in the numerator. Does anyone remember those 3 rules? 3 rules. That's the one that's the same. Yeah, see? So it's hard to remember these things because we don't care. No, I'm serious, we don't care. And that's why it's hard to remember them. So let's learn the red so we don't have to remember these. Horizontal asymptotes will never go away. Well, they go away if this is your last math class, sure. But if you're an engineer, they never go away. So memorizing 15,000 rules, and obviously you already don't remember them from not even a year ago, right? So now I'm giving you the red definition so you don't have to remember them. The rule says if the numerator has higher exponent, no horizontal asymptotes. If they have the same, it's the ratio of front coefficients. So answer over here by that has to be 3, right? 3 divided by 1 because they're both squared. And then if the denominator has the higher exponent, the horizontal asymptote is at y equal to 0, which is this case over here. Exponent in the numerator is 0 because x to the 0 is 1, and the 1 on the bottom is 1. So the bottom has the bigger exponent, therefore the asymptote was at 0. Sure. So those 3 rules still hold in all of it glory, right? But again, those 3 rules only work for rational functions. What about logarithmic, exponential, square, radical functions? What about trig? What about hyperbolic functions that you haven't even seen yet because you are not in Calc 2 yet? You're going to learn an entire new family of functions in Calc 2 called hyperbolic functions. So what about those? This is why you don't study the example, you study the theorem and definition. All right, so how do we do this without using those rules? Again, if you know the rules, great. You're going to be done with this problem in a second. You divide by highest exponent. You look at all 5 terms. You have 5 terms, 2 in the numerator and 3 in the denominator. You look at 5 terms and you find the highest exponent. Well, that's x squared. Divide everywhere by x squared. Anywhere. The highest. That's it. You're done. Just the highest. Could be anywhere. Divide by the term with highest exponent. Limit x goes to infinity. 3 plus 9 over x squared divided by 1 plus 1 over x minus 6 over x squared. Now, the step that you will always skip in the future is to give the limit to each of the 5 terms. So this becomes limit of 3 plus limit of 9 over x squared plus the limit divided by limit of 1 plus the limit of 1 over x minus the limit of 6 over x squared. And all of these are going to infinity. You will never write this step ever again because it's implied. You can just look on the left. Before I solve this problem, and we know that the answer has to be 3 because of the pre-calculus that we don't remember anymore. Let's discuss first limit 1 over x to any exponent as x goes to infinity. What happens with this paper if I divide it into 2? What happens with the size of this paper if I divide it by 2? Gets smaller. Great. So if I divide this paper by 2, meaning one half, good effort. We get this, unfortunately. Now, if you divide a half by 2, you get a quarter. The paper gets what? Smaller. If I divide it by 8, we would get this much. Divide by 16, divide by 32, divide by 64, divide by 128. What's happening with the answer as I keep dividing by a bigger and a bigger number over here? What's happening with the answer? It approaches 0. Answer approaches 0. So any limit of this form will have 0. Do you see the 3 limits are of that form over there? So dead, dead, dead. There's your 3 over 1 equals to 3. Horizontal asymptote at y equals 3. And that's the entire problem. So we start by dividing with the highest exponent and then working through algebra. You don't have to write this step, but keep it in mind. And then this formula kicks in. When you divide, right, it gets smaller and smaller and smaller. This is the result. This is the answer that you get on the other end as an answer to the division. If you divide the paper, that's what you get. So now, what do I do? Well, I mean, that's it. Let's do another example. Oh, let's write this first. Horizontal asymptotes are obeyed only at infinities. Let me first do put this on a cloud. Horizontal asymptotes must be obeyed only at infinities. This means that the function can punch through horizontal asymptote. Vertical asymptote can never be crossed, but function can punch through the horizontal asymptote locally. You are going to find an example later on in chapter 4 where we might have this situation. Vertical asymptote, a function here, and then let me just draw a horizontal asymptote in red. So ha. All right. Now, look at the black function now. There is a function that obeys asymptotes, as you can see, and this is exactly what you expect, right? But look at the middle piece. The middle piece is going to do this. Punch through the horizontal asymptote right here. That is okay. You can pierce through the horizontal asymptote locally. Horizontal asymptotes must be obeyed only at infinities. Locally, you can punch through. So, I'm going to put the blue star over here and then just put the blue squares over there. Not at infinity. So function, if it needs to, function can punch through. This will be important for section 4.3 coming up, obviously, in 2 months or less. Now, what happens if the limit is equal to infinity? What if limit x goes to infinity of f of x is equal to infinity? We call this situation in pre-calculus end behavior of the function. We call this end behavior of the function. You have 4 of these. So this is not xy graph. Oh, why I'm putting arrows? This is just a chart. Chart, not xy axis. There we go. So we can have the end behavior like this, like this, like this, like that. And these are the only 4 combinations that we can get. So this is limit as x goes to positive infinity of f of x, giving us positive infinity as an answer. And this one is limit x goes to positive infinity, where we get negative infinity as the answer. So these arrows, right, the end behavior of the function is going to go into infinity in x and y direction. So it's not going to be a finite number. It's not bounded. It's unbounded. On this side, we have the limit as x goes to negative infinity to give us positive infinity as the answer. And the limit x goes to negative infinity of f of x is going to be the negative infinity. I'm going to ask you to look at this, use the common sense, and then think of the stove at home with 4 burners. There you go. Right? So just figure it out in any way you can. Clearly, the negative values of x, right, push to the negative infinity. This goes to the left. That's what the negative x's are. But it also goes up forever, which is what positive infinity is for the answer. So motion to the left and right is x going to one of the infinities, and the motions up and down, is your answer going to positive or negative infinity? And then just put them where they belong. So now we can paint the full picture of exponential function, where one side of the function goes to 0 and has a horizontal asymptote, and the other one is the end behavior. So f of x equals e to the x, and you graph that function like this. As you examine the function, let's put the red side over here, is the limit as x goes, no coughing, to negative infinity of e to the x, what did I just say, is equal to 0. And the right-hand side is going to go to positive infinity as the end behavior. So this is the limit, x goes to positive infinity of e to the x is equal to positive infinity. Yeah. Clearly your parabola, right, is going to have two positive infinity answers and so on. So you can just plug in any function you want. Since you are so interested in trigonometry, trigonometric functions in these cases do not have an answer because they oscillate as they go to infinity. So, limit of sine x or cosine x as x goes to either positive or negative infinity does not exist. Or tangent or any. You know what I'm going to do? I'm going to put insert trig here. Any trig function. All 6 of them. They are periodic functions and they bounce either between -1 and 1 or between negative infinity and positive infinity on the y value, and they are periodic going on forever. So the limit does not exist at infinity.
Why wouldn't tangent between like negative pi or negative pi over 2 pi over 2?
I'm just waiting for you to bound it on x, and then I say, where's the infinity? Are you Chuck Norris or something?
No.
You're trying to squeeze the infinity between negative pi over 2 and positive pi over 2. That's the power reserved only for the almighty Chuck Norris. No one else. So I will agree with you that any bounded situation, you can look for vertical asymptotes, but the call for infinities, you are not allowed to bound because you can't, right? You are forced to go to infinity. As you bound, you cut those infinities off, so the entire lecture is scrapped immediately. This lecture doesn't apply in any bounded situation, only going to infinity. But the lecture is very important because when you come up with mathematical models, you want to know if mathematical model can be applied to the situation that you try to model. The first function you study for population, checking the population and so on, is the exponential model. Just having e to the kt. But we know that that model is garbage because if you let time go to infinity, your population is going to go to infinity, and we know that the planet is finite. Even if you find another planet, it doesn't matter because that one is finite too. You just wait another 2 years and there you go, right? So you don't get to bound things, right? To cut them off, because then you can't talk about infinities. If you have the situation when you talk about infinity, you are going to run into a situation when the limit is finite, which is the horizontal asymptote. Limit is infinite, where you're talking about the end behavior, which is blue over there. Or you are running into the green one, which is the periodic function, which does not have limit at infinity because it oscillates. And that's that. There's much more, but that's that. Negative infinity and positive infinity are the same point. There, I said it. They're the same point in two-dimensional space. They're different concepts in a one-dimensional number line. I added a dimension, so obviously to bend the space. Anyway, electrical engineers, hi. Let's talk about the last application problem, and then that's it, right? Why do we have a mini explosion when we short the outlet? Yes. Yeah. But why?
You drop resistance, your amperage increases without doubt.
Very good. So both things that you guys said is correct. Now we're going to do the simplified version. Ohm's law says that current is voltage divided by resistance. Now, to make the analog of what these things are, current is the flow of electrons that actually makes things work. That's where the energy is, in the kinetic motion of those electrons through the wire. Now, voltage is what makes current move, because voltage is the difference of potential. The analogous thinking here is a pipe with water, which is slanted. So now, there is a larger potential here than there of energy, so the water will flow this way. It's the same reason why the wind is created when you have a difference in atmospheric pressure. The wind is trying to equal the pressure. So there is a flow of air, there is a flow of water, there is the flow of electrons. It's a motion that has kinematics in it. So the voltage, which is 110 volt, well 118, but when you plug something in it drops to 110. So we are talking about 110 volts in the United States, or 220 where I come from. It takes me time to figure out that I'm getting electrocuted when I work over here, because it's like nothing. Yeah, the first time I got electrocuted by 220, I was in 5th or 6th grade. I knew that wood does not conduct electricity. But that day I found out that graphite is the best conductor on the planet. Much better than metal. The problem is that graphite breaks easy, so we don't make wires out of it, right? So I had my lamp like this on a desk, and there was no light bulb in it because it burned out a day or two before. And as I was doing the homework and wondering obviously about physics and other things, because who knows what I was doing, I decided to stick my pencil in there because it was off. No, it wasn't. That was the first time when I felt the 220, and it was amazing. I can tell you that. So now, when I get here, and that was just the first time, obviously. You remember the first time. In the 8th grade, I was getting zapped every other week, so because we were playing with it a lot. So, yeah. So 110 volts is what makes current flow, but only when you plug something in. Now that brings the resistance, and the resistance you can think of the material out of which the pipe is made to get the water through, or you can think of resistance as how big the pipe is, right, to let the water through. So now, as you said, as you make resistance go to 0, current is trying to shoot to infinity. Right? Now, current is proportional to temperature. There is a formula for that. So, as the current is trying to reach infinity, temperature is trying to reach infinity in a very short interval of time, so you get a little puff before the breaker switches off. Now, if you had a rogue electrician in the house, or you not knowing the code tempered with the things, well, then there's no house. Because it's made out of wood and cardboard, right? Where I come from, you call the fire department. My living room is on fire. Just close the door, it will die. It's technically what it is, because it's all concrete. So it's awesome. If anything goes on fire, just close the door and wait 2 minutes. Done. My hometown, 72,000 people, 3 trucks, and one is usually broken. I have never seen them in action. Never. Just close the door. No oxygen, the fire will go out. That's very simple. The walls cannot burn because they're concrete. Anyway. Well, that's that. Fun. Limits at infinity. I don't have any closing.